Welcome to the Deep Dive. Today we're diving into something really fundamental in electronics, the diode.
That's right.
You, our listener, sent over this diode.pdf document, and yeah, our mission is to really get our heads around this component, without drowning in tech jargon.
Think of it as cracking the code. What it is, how it works, why it matters.
Okay, let's unpack this then. A device that lets electricity flow only one way. Sounds, I don't know, deceptively simple. I've got a feeling there's quite a bit more under the hood.
You're spot on. The core idea is one-way flow, but how it achieves that is, well, pretty neat. It's a semiconductor device, usually silicon.
Okay.
Imagine it treated in two specific ways. One part's a P region, the other's an N region, and where they meet. That's the crucial bit, the PN junction.
Right, the junction.
And right around that junction, a little zone forms, the depletion region.
Yeah.
We also call the P region the anode, and the N region the cathode.
Anode and cathode, got it.
And this whole setup gives it that key property. Conducts easily one way, resists strongly the other, like a one-way street for electricity. It's kind of amazing how this tiny region controls everything.
A one-way street, controlled by this depletion region thing. Interesting. So how do we, open the gate, get the traffic flowing? The document mentions forward bias.
Exactly. Forward bias is how we encourage flow. We apply a DC voltage, the source calls it VBIS, connect negative to the N region, the cathode, and positive to the P region, the anode. Figure 2 in the doc shows this clearly.
Right.
But, and this is important, that VBIS has to be enough to overcome what's called the barrier potential. Think of it like a small energy hill.
A hill. How high?
Well, for older germanium diodes, it was about 0.3 volts.
Yes.
But for silicon, which is nearly everything now, it's around 0.7 volts.
0.7 volts.
Yeah.
Okay, so you need that minimum push to get electrons over the hump. And what happens then, once you give it that push?
Once you cross that 0.7 volt threshold, things really get moving inside. The negative side of the VBIS pushes the free electrons in the N region towards the junction.
Makes sense.
And the positive side attracts the holes. Those are like missing electrons acting as positive charges in the P region, also towards the junction. Figure 3 illustrates this nicely.
So electrons from one side, holes from the other, meeting in the middle.
Pretty much. And as they move towards each other, that depletion region, the barrier zone, actually starts to shrink.
Ah, okay. So the barrier gets smaller, making it easier for current to pass through. That makes sense visually.
Precisely. Electrons and holes combine at the junction, and you get a continuous flow. What's fascinating here is how the applied voltage essentially shrinks that electrical barrier within the material itself. It's actively changing the physics right there.
Okay, cool. So that's opening the gate. Forward bias. What about closing it, stopping the flow?
Yeah.
That's got to be reverse bias, right?
You got it. Reverse bias is just flipping the connections. Now, positive VBIS goes to the N region, and negative VBIS goes to the P region. Like in figure 4, we're pushing the wrong way, essentially.
Okay, swap the leads around. What does that do to the depletion region?
It does the opposite. Instead of shrinking, it gets wider. The positive voltage pulls electrons away from the junction on the N side.
Pulls them away.
And the negative voltage pulls the holes away on the P side. This leaves more charged ions behind in the depletion region, effectively making that barrier bigger and harder to cross.
So the one-way street is now firmly blocked.
Pretty much. Very little current gets through. Ideally 0. But in reality, there's always a tiny, tiny leakage current.
Okay, very small leakage. But then the document mentions reverse breakdown. That sounds like the blockage fails somehow.
It can, yes. And this raises an important point. If it blocks current, is that the absolute end of the story? No. If you keep increasing that reverse voltage, pushing harder and harder in the wrong direction, you eventually hit a point called the breakdown voltage. And then suddenly, the reverse current shoots way up.
Whoa, so the dam breaks, current floods through backwards.
No, kind of like that, yeah. It's often due to something called the avalanche effect. Imagine one tiny minority electron getting accelerated by that huge reverse voltage.
Yes.
It slams into an atom, knocking more electrons free. Now you have more electrons getting accelerated, hitting more atoms. It's a chain reaction. Avalanche.
The avalanche effect, like dominoes falling.
Exactly. And while it sounds destructive, and it can be, some special diodes are actually designed to operate safely in this breakdown region for voltage regulation. It shows that even seemingly solid barriers have limits.
Interesting. So even the off state isn't totally absolute, which brings us to the voltage current characteristics, the VI curve stuff. This sounds like the map of how it behaves.
It is. It's the graph showing current versus voltage. Super important. Let's look at forward bias first, figure 5. As you increase the forward voltage, V, hardly any current flows until you hit that barrier potential.
The 0.7 volts for silicon.
Right. Then, just past that point, the forward current, if, increases very, very steeply. Even small voltage increases cause big current changes.
Wow. Yeah, it really takes off there.
And notice the slope isn't constant. That means the resistance isn't fixed. It changes. We call it dynamic resistance.
Okay, so not just a simple resistor, it's dynamic. Got it. What about the reverse bias side? Figure 6.
In reverse, as we increase the reverse voltage, you see only that tiny leakage current flowing. Almost nothing.
Right, the closed valve.
Until you hit the breakdown voltage, VBR. Then the current suddenly skyrockets downwards on the graph, indicating a large reverse flow.
And the voltage across it stays pretty much the same during breakdown.
Yeah, largely. Usually you want to avoid operating there unless it's a specific type of diode designed for it, like a Zener diode.
Okay, here's where it gets really interesting for me. It's not just on or off. There's this whole, curve describing its personality in both directions. It's way more nuanced.
Absolutely, which leads perfectly into diode models.
Right. Why do we need different models? If we have the curve, isn't that the whole picture?
It is, but the curve can be complex to work with mathematically in every single circuit analysis. So we use simplified models as approximations. The doc shows 3.
Okay, lay it on me.
First, the ideal diode model. Figure 7. Super simple, forward bias. It's a perfect closed switch. Zero voltage drop, infinite current allowed. Reverse bias, perfect open switch. Zero current, infinite voltage blocked.
Like a theoretical light switch. On or off, no in between.
Exactly. It completely ignores the barrier potential, dynamic resistance, reverse current, everything real world. Useful for maybe a first basic concept check.
But probably not for designing actual circuits.
Generally not, no. That's why we have the practical diode model, figure 8. This one does include the barrier potential.
Ah, the 0.7 volts.
Right. So in forward bias, it acts like a closed switch plus that 0.7 volt drop. Still ignores dynamic resistance and reverse current, mostly, but it's much better for many calculations.
Okay, so when you're calculating current, you'd use Ohm's law, but first subtract that 0.7 V from the source voltage. Because that EF's VI's AVF our limit equation.
Precisely. You account for that initial voltage cost to turn the diode on.
Makes sense? And the third model?
The complete diode model, figure 9. This is the most accurate. It includes the barrier potential and that small forward dynamic resistance and even a very large internal resistance to model the tiny reverse leakage current.
So that one tries to capture almost everything from the VI curve.
As much as is practical in a model, yes.
So what does this all mean then? We have these different ways of thinking about a diode. Why all the options?
It's really about trade-offs. Simplicity versus accuracy. The ideal model. Easy, quick, good for basic ideas. The practical model. A good balance, widely used for common analysis. The complete model. Most accurate, but makes the math harder. You pick the model based on what you need for the specific circuit you're looking at.
Right tool for the job. Okay, that clicks. Now let's talk applications. Where do we actually find these things doing work? The doc starts with DC power supplies.
Absolutely fundamental there. Think about anything you plug into the wall that runs on batteries or low voltage DC, your phone charger, laptop brick.
Yeah.
They all need to convert the AC wall power into DC. And diodes are the heart of that conversion process in the rectifier stage. Figure 11 shows a typical block diagram.
Okay, transformer, rectifier, filter, regulator. And the rectifier bit, that's where the diodes live.
That's their main job there, taking that back and forth AC and making it flow in one direction, even if it's bumpy DC at first.
Bumpy DC, I like that. So the document dives into rectifiers next. Half-wave rectifiers, figure 12. Looks like the simplest one.
It is. Just one diode. When the AC input swings positive, assuming standard connection, the diode conducts. When it swings negative, the diode blocks.
So you only get the positive humps of the AC wave, chopping off the bottom half.
Essentially, yes. The output is this pulsating DC, but only using half the input waveform. The output frequency is the same as the input AC.
And the average voltage, VAVG, is only about 31.8% of the peak input, VP. Seems kind of wasteful.
It is inefficient, yeah. You're throwing away half the power. Plus, the diode needs to withstand the full peak reverse voltage, the PIV, during the off cycle.
Okay, so half-wave is simple but not great. That must be why we have full-wave rectifiers.
Exactly. Much more efficient. They managed to use both halves of the AC cycle to create the output DC.
Both halves? How?
The output current flows in the same direction through the load during the entire AC cycle. The output frequency is now twice the input AC frequency, and the average voltage is higher, about 63.7% of the peak. Figure 14 shows that double hump waveform.
Twice the humps, much better average voltage.
Okay. And there are different ways to build these full wave ones. The doc mentions center tapped, figure 15.
Right. The center tapped version uses a special transformer with an extra connection in the middle of its secondary winding. And it uses two diodes.
Two diodes.
One diode handles the positive half cycle, the other handles the negative half cycle. But because of that center tap, they both push current through the load in the same direction. Figure 16 tries to show the current paths.
Okay, requires a special transformer, though. What's the other the bridge full wave rectifier. Figure 17. That looks like 4 diodes in a diamond shape.
It is. The bridge rectifier is probably the most common type now. Very clever arrangement of 4 diodes.
4.
Yeah. It directs the current through the load the same way, regardless of whether the AC input is positive or negative, without needing that special center-tapped transformer. Very efficient and versatile.
So that's likely what's inside my phone charger, then, some kind of bridge rectifier.
Very possibly, yes. Along with filtering and regulation, of course. They're workhorses. Cool. Okay, so rectification is a huge job for diodes. What else? The doc moves to diode limiters, clippers. Figure 18. Sounds like shaping signals.
Precisely. Limiters or clippers are used to chalk off parts of a signal that go above or below a certain voltage level.
Chop them off. Why?
Could be to protect downstream circuits from excessive voltage, or maybe to deliberately shape a waveform. You can clip the positive peaks, the negative peaks, or both.
And you can set the clipping level.
Yep. By using just the diode's forward voltage, around 0.7 V, or by adding a DC bias voltage, or using a voltage divider, like that Vout equation shows, gives you control over where the clipping happens.
And example 2 shows this in action, right? Clipping the negative part.
Exactly. In that example, they set it up so the diode turns on and effectively shorts the output when the input goes more negative than about man equal 0.7 V, but the resistors shift the actual clipping point.
So the calculation shows it clips at negative 9.09 V instead of the full negative 10 V peak.
That's right. It limits the negative swing. You can see the flat bottom on the output waveform. It's like setting voltage boundaries.
Okay, so clipping for protection or shaping. Useful. Next up, diode clampers. Figure 19, what's their job?
Clampers do something different. They don't remove parts of the signal. They shift the entire AC waveform up or down the voltage scale. They add a DC level.
Add DC. How?
It usually involves a capacitor and a diode. The capacitor charges up to roughly the peak voltage of the AC signal minus the diode drop.
Okay.
Then, that charged capacitor acts like a small DC voltage source in series with the signal, effectively pushing the whole waveform up or down.
So the AC shape stays the same, it just rides on top of a new DC baseline.
Exactly. Whether it clamps positively, shifts up, or negatively shifts down depends on which way you connect the diode.
Huh. So you can take an AC signal that swings positive and negative and clamp it so it always stays, say, above 0 volts.
Precisely. Very useful in things like video signals or some communication systems where you need to restore a DC reference level that might have been lost.
Clever. Okay, one more application here. Voltage multipliers. Figures 20 and 21. These sound powerful.
They can be, in a specific way. They use diodes and capacitors, often leveraging that clamping action we just talked about, to produce a DC output voltage that's a multiple, double, triple, quadruple of the peak AC input voltage.
Without needing a bigger transformer.
That's the main advantage. They use stages of diodes and capacitors charging each other up in sequence. Figure 20 shows a half-wave doubler, Figure 21 a full-wave doubler. You can cascade these stages.
So you can get high DC voltages from a lower AC source. Where would you use that?
Typically in high-voltage, low-current situations, think older CRT TVs needing high voltage for the picture tube, or scientific gear like particle accelerators, certain types of power supplies. It's a neat trick for generating high V without bulky iron.
Resourceful indeed.
Yeah.
Okay, and lastly, the document just briefly touches on diode packages, just the physical forms.
Yeah, just a quick mention that they come in different shapes and sizes and usually have a marking, like a band or a K, to show you which end is the cathode, the in-region side.
Right, so you don't connect them backwards by mistake. You see tiny ones for surface mount, bigger ones with heat sinks for power application.
Exactly. The package often depends on how much current and heat it needs to handle.
Okay, so let's try to wrap this up. Diodes. They're these fundamental one-way electronic gates made from semiconductor stuff.
Right, the p-in junction is key.
Their behavior is actually pretty nuanced, depending on forward bias, reverse bias, and even that breakdown point if you push too hard in reverse.
And we use those models, ideal, practical, complete to help us analyze them in circuits, balancing simplicity and accuracy.
And they're just crucial for so many things. Converting AC to DC in power supplies using rectifiers is huge.
Absolutely essential.
And then shaping signals with limiters, shifting DC levels with clampers, even multiplying voltages. It's way more than just a simple on-off switch. There's a whole world packed into this tiny component.
There really is. And maybe this raises an interesting question for you, the listener. Now that you've seen the surprising depth behind this seemingly simple diode, what other basic components in technology might hide similar richness? Resistors, capacitors, transistors. Maybe take a second look at those fundamental building blocks sometime. You might be surprised what complexities lie just beneath the surface.